Well, thanks, Inti, for inviting me. It's always fun to talk to people from all over. Yeah, and thanks for all the kind words you said about me. There'll actually be, I've realized when you were introducing me, there's no field theory in this until the last slide, not counting the conclusion slide. Then there's a bit of field theory, but everything is on the lattice. Everything is very explicit. So I'll try and, I'm not going to give you all the details, but I'll try and be very concrete. And so what I'm going to talk about is a couple papers that just came out with Luisa Eck, a student here at Oxford, and a crucial technical thing that I'll say a little bit about as we go on, and we certainly used it, was a very long paper I wrote with Dave Assen and Roger Mung on topological defects, and I'll say a little bit about that as we go along. And yeah, I guess this is now a philosophical statement here. One of the things I like to do, and I think the problem I'm going to tell you about gives a really lovely example of, is a connection between formalism and reality. And this is what, well, I think I've tried to do my whole time, even though sometimes maybe I spend a lot of time on the formalism. I always have the real life in the back of the mind. And in particular, Rydberg atom arrays have really provided a superb way to understand a lot of interesting physics, and both experimentally and theoretically. And the experiments have actually been ahead of the theory. They've seen things that theorists hadn't really thought about yet in a strongly correlated system, in particular because you can really tune the interactions of the systems. So I'm not going to say anything about what the experimentalists do. I know very little. I'm just going to view this as a way they can fine-tune certain kinds of quantum systems. So in particular, what I'm going to talk about today is systems where you've got atoms. They're a two-state system. It's either not excited or excited, is what they do in a real experimental system. So it's a two-state system. But for practical purposes, just think of it as a hardcore boson, meaning either the site's empty or there's a hardcore boson there. But then in the Rydberg-blockade, at least in the simplest version I wrote here, is that neighboring sites cannot be occupied. And so so if you wish, it's a fatter boson. So it's a hard core, but where the core extends again. So I'll discuss this example there, and already a lot of interesting things have come up experimentally in the last 5 years or so. But this picture is a really old one. One from a paper I wrote long before experimentalists studied these Rydberg-blockade. A paper with Krishnendra and Gupta and Sabir Sachdev 20 years ago or so. And so what we were doing, we had different experimental motivations, but what we were doing is taking, so we were taking these hardcore bosons subject to the nearest neighbor blockade. So this annihilates, and that creates a boson on the sites of a chain, but such that nearest neighbors can never be occupied. One boson per site at max, but in fact, not even nearest neighbors. And then there's chemical potential, and then there's a next nearest neighbor interaction. The N is just the density of it. So the kind of the simplest Hamiltonian you can think of bosons subject to this restriction. You could add longer range interactions, but this is all the short range stuff. And so we draw this phase diagram, and towards the end, I'll review some of this physics because we're going to go off on some diversions, but just comment here. Okay, again, because of the nearest neighbor, forbidding nearest neighbor bosons, kind of one kind of order you get would be the Z2 ordered here. Another would be the Z3 ordered, where there's a particle on every third site. For the Z3 ordered, particle on every other site. There's some transitions that I'll say, and then there's a critical transition, all that. I'll say a little bit more of that about how this goes at the end. But the thing to think, the Z2 ordering is translation symmetry breaking. There's no other symmetry in this problem. There's no particle number conservation. There's not even sort of a Z2 symmetry. The only symmetry of this particular Hamiltonian is translation symmetry. And so that's the only thing that you can break. And so this is 2A. So you get a nice phase diagram. Now, where this came up, so people, Lucan's group, and now many others, have realized this and much more general models experimentally, and they observed this interesting behavior that goes by the name of quantum scars. They observe very long-lived quantum effects. And the model here at the origin, basically, you just tune tune U and V to be 0, is called now the PXP model. The name is because X is basically, you can think of annihilating creating particle as the sigma X, the Pauli matrix, and then the P is the projector that forbids nearest neighbors from being occupied. So anyway, so that's called the PXP model, and that exhibits quantum scars, but it's from our old point of view, this was just one point in the disordered phase in this phase diagram. Turns out only the scars only really happen at this point in close to, which is slightly understood, but maybe not fully. So anyway, one thing to say, and I'm not going to talk about it anymore. You can tune these interactions further, do next nearest neighbor interactions, or make the restriction longer, so and get other orderings again, which are understood theoretically and have been seen in experiment. So the experiments right away.
So can I ask you just a very simple question? Maybe
please.
you go back just to understand. Maybe I'm just being sort of lost by basics, but so they are hardcore bosons, right?
Right.
So at the origin, you have basically what, a transverse field Ising model, or?
No, so because the transverse field Ising model has Z2 symmetry. So this is really this annihilates and creates the bosons. So you don't have boson number conservation. You don't even have a Z2. It doesn't create them in pairs. It literally just annihilates and creates the bosons.
I see. Okay.
And then these are simply interactions.
I see.
That's all. So this is, yeah, you can, if you read down here, I didn't mention it, I'll talk about later. This blue dashed line is critical Ising transition, but that's basically because the reason, there's only so many transitions under the sun, and this is a transition from Z2 order to disorder. So what else could it be than Ising if there's no other symmetry? And well, that's not a great argument, but in this case, it's a correct.
I know that. It's okay. But
so that's
why is it happening for B negative? Like, is it B negative not attracting the bosons, or?
No, so right. So what happens here? So if you do this, so V negative makes them attractive. So that's down here. But then so we can let's just set U equals 0. So there's no chemical potential. Right. So you think what happens is, so if I make V positive, it's disordered. So when we're up here, let me get the pointer. So up here for V positive, you then so V positive, you very strongly disfavor the boson. So basically, the ground state way up here is just empty.
I see.
Because, well, or very, sorry, I shouldn't say empty, dilute, because you can create and annihilate them, but they have to stay apart. So it's very dilute.
I see now. But
now, okay, you make them less unattractive, but here you're still disordered, because here there's nothing to constrain them. You're just annihilating, creating them. It's subject to this constraint. So this is not a trivially solvable model, the PXP point here, because it's not trivially solvable because the restriction that they can't be next to each other. This is not it's not even integrable. Can't solve it. But it does have this nice behavior, this quantum scars, which is a story I'm not going to talk about. You should definitely invite someone to talk about that.
Very good.
Zlatko Pavic can give you a great talk on, or Max Irvin. Give great talks on how that goes. But then, of course, now you make it attractive as you move down this line here. And then you get this Ising transition where it favors. What happens up here is funnier. Here you're making V positive, so they want to repel each other, but you make U negative, so you want a lot of particles. So what they settle into.
Right, I see. So they go into some kind of close packing.
Yeah. And so actually, this is a good setup. Now I can say, but now if you do the latter, which is what I'm going to get to eventually, it's a lot more complicated. You can have a lot of interactions, and you can imagine all sorts of orderings. Anyway,
Very
so
good.
that's the story there. Okay, but that's what's getting. Sure, any other question? I'm happy to be derailed by questions. So please interrupt if you like.
Very good.
Okay, right. So that's right. Oh, right. So the point is, the experimentalists can make all different arrays and have control. These 2D arrays are, I think, pretty easy for them, and they do lots of things. And so there's experiments, but in particular, there's been a little bit of theory on there. And one prominent thing is Ruben Verison and collaborators proposed that there might be a spin liquid phase. Basically, they showed in these Rydberg systems that you could realize the quantum dimer model, the square lattice quantum or triangular lattice quantum dimer model. I forget what lattice they claim, but you do it on any non-bipartite lattice, and you can get toric code topological order. And they propose doing that. The experiments at least see signatures of it. I think some people are arguing whether they've seen it or not, but at least it looks promising to actually. But the theory is pretty difficult because even like I said, in 1D, it's not integrable. We even that phase diagram I showed you on the previous slide there's some analytic things to do because well, there's some integrable lines and so forth, but even that you can't solve, although I think you can understand the physics pretty thoroughly. But then for the ladders, it's just much more complicated. A few things, nice things people have said, but it's very much in its infancy, and also it's kind of bewildering. You don't know where to start. You can add a lot of interactions, and everything looks very complicated. So what we did was basically find integrable case of the square ladder. And this model sort of existed before, but this is what Luisa and I described in depth in our pair of papers. And then you can use that very much to anchor your understanding. But in particular, one thing that you learn by thinking about this special integrable model is that there's all sorts of interesting dualities and non-invertible symmetries. I'm going to tell you a little bit about how that goes as we go on. And so using those dualities and non-invertible symmetries, and if you don't know what that is, that's fine. I'll try to explain that to you. So using these things, we can then map out this phase diagram. We still have to use a lot of numerics and all sorts of other stuff. So I'll go through that. So most of the talk, I think time-wise, is actually going to be devoted to just sort of how we got there. So it's going to be formal for a while. We'll try and make it as user-friendly as I can and just give you an overview of the formalism. Again, please, if I sound script, please interrupt. And then at the end, the payoff will be mapping out this diagram via all the techniques that we learned about and that I'll try and explain to you in this talk. And one of the key ones came from this paper with David and Roger. In particular, the way to implement non-invertible mappings and symmetries is via topological defects. And the way that goes, so this is just a schematic picture. And so, again, I'll come back to this in more detail as we go on, but I just wanted to give a very schematic picture of what these things are. So, okay, so you got some lattice model. Let's just pretend it's a 2D classical lattice model at the moment. Just think a 2D classical lattice model, but we put defects in it, and that's what these lines represent. And there's different kinds of defects in there, and they're topological. What that means is just the partition function and their presence doesn't depend on any deformation. So I move them around. They can branch and they can all that. But the point is, if now we go from this 2D classical picture to a 1D Hamiltonian, so say we call the direction time. So if I make this direction time, say, then I have a Hilbert space, sort of horizontal. Actually, yeah, it's better to use the line than they tried to draw for me. And So we have a Hilbert space, a horizontal Hilbert space. And what we can do then is think about time evolution in the presence of these defects. And what we find is, in fact, that these must commute with the Hamiltonian, because I just told you a few seconds ago that they're topological. So that means that the partition function doesn't depend on their location. And so thus, if I can deform them, I can deform them backwards and forwards in this new time direction. And so they must commute with the Hamiltonian. But what you find sometimes, the theory can be different on one side of the Hamiltonian versus the other side of the Hamiltonian. So maybe this is theory A and this is theory B, and that's often what we call duality. And if you're familiar with Kramer's 1A duality in the Ising model, the low temperature and the high temperature. So this over here, with the right kind of defect, this phase could be the high temperature phase, and that could be the low temperature phase, and so forth. And so these provide, you can think of it, again, acting on a Hilbert space as providing mapping between these models. And the key buzzword these days is non-invertibility. So our string theory friends, that was terrible. Our string theory friends have been studying this a lot recently, because they have all sorts of interesting field theories where you can construct these non-invertible symmetries and learn how they do there. And they've learned all sorts of new things, new ways of realizing time reversal symmetry, if you allow time reversal to be non-invertible, for example. So all sorts of cool stuff there. And so I'm going to tell you about some things. And so this symmetry is really useful in understanding the Rydberg-blockade ladder that I'm going to tell you about. So, okay, so here's the outline of the model. So the first thing is, so again, like I say, it's going to be formal for a while, but I hope not too formal. I hope it's comprehensible. And so I'm going to take the XXE chain, which I hope everyone has at least heard of, something much more familiar than this Rydberg-blockade chain I wrote down. And I'm going to rewrite it in terms of an algebra, and I'll say what I mean by that. And what this buys you is 4 Hamiltonians that are related to each other. They're all integrable. XXE is integrable, and all the ones we obtain in this fashion are integrable. And well, those are their names, and one of them is our friend, the Rydberg-blockade ladder that I described. So that's how it. So then I'm going to explain how to map between these theories using these non-invertible mappings I just quickly outlined. And then, okay, then finally I'm going to get back to the Rydberg. So like I said, the bulk of the talk will be explaining this, but I'll make sure to leave at least 10 minutes and maybe hopefully 15 minutes at the end to get back and explain the physics of the ladder, this integrable ladder. But then learning about that, we can now do this 3-parameter phase diagram. And okay, so that's the story, and that's what we'll go through. Okay, so first let me tell you about this algebra and what that means. So there's a really famous old paper for now several reasons by Temperley and Lieb, 2 of the greats in StatMac and mathematical physics. And what they did, and this isn't always known even for people who uttered the words Temperley-Lieb algebra thousands of times in their life, what Temperley-Lieb actually did. So here I'm telling you what they actually did. And what they were doing is looking at different lattice models. So this one here, they call it the Whitney polynomial for reasons I never quite understood. What we would call it now is the Potts model partition function. It's Whitney polynomial. And then there's problems of ice, which are the classical version called the 6-vertex model, but that's the XXE chain. And they were deriving relations between them. And the way they did this, well, they wrote things in terms of graphs, but in particular, what they did is they took the transfer matrices of these classical models, and they wrote them in terms of operators. So transfer matrix, just think of a Hamiltonian. So you can, everything I'm saying here works for Hamiltonian. So you've got a Hamiltonian acting on some space. And so, you know, we're used to writing Hamiltonians in terms of operators. We've got Pauli matrices and products of Pauli matrices. And these are operators. And, well, if you're just using Pauli matrices, well, either each term commutes with another term or it anti-commutes. And if you take combinations of the terms, more complicated things can happen. But what they did is they showed there's a certain way to write all of the models I just mentioned there. And so we write them here. Ones you may have heard of, the Potts models, the XXE model, and some people like me like loop models. So they took all these different looking, completely different models, and they showed you could take the Hamiltonian for these models and write it in terms of generators of some algebra. The algebra they wrote down is called the temporal-Lieb algebra. I'm not going to write it down because I'm not going to use it, but the idea was brilliant. And then they showed these different models could all be written in terms of generators satisfying the same algebra. And thus you might expect them to be related. And what they then derived was then, as a consequence, you could derive linear identities between their partition functions that satisfied these different relations. And so where the other place where people have heard temporal-Lieb, and I'm going to mention this quickly because it's going to come back again, is when Vaughan Jones was inventing Jones polynomial. He actually independently reinvented the identical algebra the temporal-Lieb had, and he was honest and named it the temporal-Lieb algebra, even though he some people tried to add his name to it, which probably would be fair, but it never stuck. So it remains the temporal-Lieb algebra. But in particular, the connection is via loop models. So there's also some interesting stories. I gave lots of talks on that over the years, which a few of you may have seen at random points on how these lattice models are related to the things that Jones did. But the important part for what I need is so Jones did the Jones polynomial, then people came up with lots of generalizations, and the key buzzword there that I'll come back to later in the talk is fusion category. This enables you to do this. All right, so that was a slight tangent, but I think one that's really important that people know. There's a whole huge story out there that we're going to exploit later on in the talk. Okay, so here's the XXE chain, which I hope anyone's seen at some point before. Just a chain of two-state systems. All of them always take periodic boundary conditions today. And X, Y, and Z are just Pauli matrices for reasons that I'll mention later. I take these degrees of freedom to live on the half-integer sites, and as opposed to integer. And so this just flips spins on adjacent sites. And there's a U1 symmetry of this. I don't think I wrote down the generator, but since this you can turn into sigma plus and sigma minus sigma plus, these two terms together, there's a U1 symmetry corresponding to the sum of Z. So it's a beautiful, famous U1 model that's very well understood, although still lots of interesting things people keep learning. Okay, so I'm going to write this model in a funny way. So this is in the spirit of temporal-Lieb, but it's not the way they did it. I'm just going to say something, well, a priori, this is kind of very low content. I have a Hamiltonian. I write it as, I take all the terms here. I call that S. And I take the terms in front of the delta. So delta is just a coupling. And I write them in terms of B, this B. So that's all. This is a completely trivial thing so far. But I mentioned with the temporal-Lieb, but they showed now these things, they satisfy some algebra. So this isn't their algebra, it's a different algebra. So first we can look at the algebra. Well, okay, there's a trivial one that if they're far enough apart, they commute with each other. That's just completely obvious that they commute with each other. But now less obviously, you can ask, well, okay, what happens when they're on the same index J? Well, then you can see, did I say that? Yeah. S and J at the same site commute, Sj and Pj commute with each other. But the less obvious ones are the other ones, which is that, again, you just work it out. It takes you about 5 minutes to do this once you know, although it took me quite a while to find kind of the minimal nice form of these things. So pretty obviously, that thing I wrote on the previous slide was a projection operator. This thing over here, it's a projection operator, so that squares to itself. Turns out, sorry, I said that they do commute, but more importantly, when you just multiply on the same site, you get 0. This one squares. Those are kind of trivial. These take a few minutes to do, and there's other ways to write them. But anyway, so you just work it out. it satisfies that algebra. So in case there's a few of you that are familiar with temporal-Lie, notice this algebra has no parameters, as opposed to temporal-Lie has a parameter. So the representation theory of this is maybe easier than temporal-Lie, so not nearly as rich. This parameter here, we do have a parameter, but notice it's not in the algebra, just in the Hamiltonian, just the relative coefficient of these two terms in the Hamiltonian. And so now just using this algebra, from now on for the most part, just forget it's XXZ. You just have these generators, they satisfy this algebra. You can check just satisfying these relations that the P's commute with each other. The S's don't, as you can see. And then PS on adjacent PS, P and S have this commutation relation there. You can take this one as fundamental if you want to get rid of one of these. And take this as fundamental if you'd rather. I like that form better. So for those who know something about integrability, you know what the Yang-Baxter equation is. If you don't, just trust me. What happens is you check these certain Boltzmann weights or quantum Hamiltonian. It satisfies this interesting property called the Yang-Baxter equation. If it does, the model's integrable. And the key thing I want you to take home, even if you don't know what the Yang-Baxter is to prove it's integrable. All you need is this algebra in this box here. Well, the fact that they commute further apart. Any model is then integrable for any delta, for any S&P. So that's why you use these algebras. You can forget the X's and the Y's and the Z's. You can just do that. So that's this algebra. So now using this, you can find for a quartet of Hamiltonians, including XXC, so 3 more Hamiltonians that all.
So can I ask you
a
very basic question, Paul? So I'm not an expert in integrability, so this might be a very dumb question, but anyway, at the expense of.
Yeah.
So when something is sort of integrable in this sense, okay, in this that satisfies these Yang-Baxter equations, it doesn't mean that I can solve the full. That I know all the states, right? That I know
no
ground state and all the states. So
it means that it has, at least in principle, although often you can't even write them down in closed form, means it has this sort of hierarchy of commuting conserved quantities. So that means one might then hope to be able to do exact computations. Practically, what you can often do is compute like the ground state energy or the free energy if you go to finite temperature. That you can usually, but not always do. There's this, sometimes you can get the beta ansatz to work. In this case, you can. You can in XXE get the beta ansatz to work, and then you can understand what the low line excitations are. But it's not a guarantee of anything. People will tell you, I've seen it so many times in talks. I hope none of the people are listening today. I guess it'll be recorded. That's right. I'm all people say, "Oh yeah, it's all cookbook." Reshetikhin and Fadeev worked all this stuff out in the 80s, and this is total and complete rubbish. What Reshetikhin and Fadeev did is it's fantastic, but Reshetikhin and Fadeev would not say, "Oh, we can now solve everything," because well, sadly, Fadeev's not with us. Reshetikhin still is, and he's still working hard, trying to drive consequences of these things. So, sort of in principle, lots of things can be done, but in reality, you can't. There's lots of models, in particular ones, to be technical, ones that are elliptic solutions of the Yang-Baxter equation. Essentially, except in one case, we don't know anything about these. I shouldn't say we don't know anything. We know very little about these models. Baxter spent his career inventing tricks, brilliant tricks, to actually extract information. But no, it doesn't tell you everything, but it does tell you some useful things, and sometimes you can. It does give you a lot of useful info, but certainly not everything.
Okay, thank you.
Good. Any other questions? Right. Okay. So here's now another model that satisfies the same algebra. So we just write S and P. So I didn't write it. S is just these terms here, and then P is the thing there. And you can just check, remember the 1/2 in front, but then you just check that it satisfies that algebra I wrote down. I knew why it would. There's some stuff I'll mention later, but in this case, it's just easy to check. And if you want to understand what this is, in fact, this ZXZ kind of thing comes up when people study SPT states. So I think it's most illuminating to write this as two coupled chains where, because notice this is J minus one and that's J plus one. So we make one chain for the odd sites, one chain for the even sites. So the one there is just the nearest neighbor interaction. And then there's an interaction around a triangle. The sign of the spin flip here depends on whether these two are the same or different, or you can think about it as spin flip with diagonalizing sigma x if you rather. And then this is just the spin flip here. And the one is to make this thing projected. And so you can think of it as two transversely Ising and satisfies exactly the same algebra. So you expect they have properties in common. But I emphasize, so when I put equivalence in quotes, because they're closely related, but not the same thing. For example, there's not a U1 symmetry that's Hamiltonian. There is of XXE. Just the way it is. There's, well, we'll talk about it. There's maps between them, but they're not exactly the same. But they are closely related. And I'll be more precise about what I mean by closely related. So there's another example that maybe I'll flash. So in the interest of time, I'll just flash through. You can write the three-state Potts chain, a three-state antiferromagnetic chain such that nearest neighbors, so it's three states, which I'll call A, B, and C per site. Lost my cursor, there we go. So three states per site, but nearest neighbors that are the same are disallowed. So you don't allow those, you don't allow those, you don't allow those. And then there's a simple Hamiltonian, basically S just flips it. If it's allowed, without restricting this rule that no nearest neighbors have to be different. And then the other term gives an energy if you can't flip it. And this turns out to have a nice graphical interpretation in terms of the domain walls. So I just went through that quickly because it fits nicely into our story. And it also leads to the next thing. So before I get to the Rydberg one, which I will get to next, now this is the most formal, I think, slide in the thing. So what happens when you look at that last example, if you know some stuff, you say, oh, well, all right, this kind of thing comes up elsewhere. And so back to this Jones story I mentioned. So I mentioned there were lots of generalizations of the Jones polynomial, essentially for any Lie algebra and any integer. In fact, this is a special case. The case we're talking about is the Jones polynomial. So that algebra I wrote down, even though I don't think before us anyone ever written it down the way that in terms of those S's and P's that I wrote down, is equivalent to an algebra that people wrote down. And it comes in this whole story. It's called fusion categories, and it's a way of generating, well, a variety of things, both integrable models and solutions of the Bray group relations and the Reidemeister group, but not polynomials. So it's a whole huge story, and that's the story that Jones started. But I have to tell you very little, but I need this one bit. And so fusion category is comprised of objects that obey fusion rules, a lot of other interesting stuff too, if you've heard to talk on that. But so just objects, we're going to give them labels. And so the best way to think about the simplest fusion categories have something to do with a Lie algebra. And these are just, the objects are the representations of that Lie algebra. So that's why we're doing SU2. And so then the things are, 1/2, sorry, 1/2, we should have had this down, 1/2. 1, sorry, we got 0, the identity, and so forth. But the catch is when this level 4 thing here, this subscript there, means that you don't have all this truncates and truncates at k/2, where k is that thing there. So now when you do the fusion, so we just mean the usual angular momentum multiplication of SU2, or more generally the rules of representational rules under tensor product of this Lie algebra. So then you get, so let's start with this. Okay, 0 is the identity representation. So you take the tensor product with the spin 1 representation, you get spin 1. And probably everyone here. I'll tell you. Take 2 spin 1s, and you get 0 plus 1 plus 2. But now where the truncation comes in for level 4, well, we have a spin 2 representation, but we fuse it with the spin 1. We don't get 1 plus 2 plus 3, what we normally would get. We just get 1. And that's the truncation that happens in this fusion category. So otherwise, we need these fusion rules for the following reason, because first I'm going to draw a picture. And so I did the spin a half ones over here. But what this picture just means is just a picture way of representing fusion 1. So here is the singlet representation of SU2. Here's the spin 1, here's the spin 2. And I just draw a line connecting the dots if the two are connected by fusing with 1. So I fuse 1, it's in 1. So the line there is 1, so that fuses that. The 1 times 1 gives me itself. That's the circle here. And then gives you that, and gives you that, and so forth. So these are nice pictures to do it. Now, why did I tell you this? So the reason I told you this was the fusion category gives other Hamiltonians whose generators obey the same algebra. And that's the Rydberg chain. And the way it works is the following. You take the degrees of freedom. So we got a chain, and I'm going to go through this really carefully in the slide. So if it doesn't if you don't completely understand the slide by then, please ask, because it's crucial. So I set up some rules, and so here are the rules. I say their degrees of freedom are, again, I'm going to label them 0, 1, and 2. And I'm going to make these adjacency rules. We say adjacent heights on a chain have to be adjacent on this diagram I just got from SU2 level 4. And so this is an allowed configuration, because notice 1 can be adjacent to anything. It can be adjacent to itself, it can be adjacent to 0. But if I have a 0, it can only be adjacent next to 1. Now, if I didn't screw up, I gave a version of this talk where I screwed up this thing before. I think I got it right this time. So an allowed configuration as you go down a chain would be this. Okay, so the reason we do this is because when you build a lattice model in this way, you get lots of nice things out. So that's why I quickly introduced these fusion category rules and why I quickly did that. All right, so anyway, so what we do is then this is an allowed configuration there, but now this configuration is that of an integrable Rydberg-blockade ladder. So in particular, so now this is the same configuration right there. If I have a square ladder, and if I take each rung of the ladder, if the rung is occupied by no particles, that's the 1. If it's a particle on the top rung, I give it a 0. If it's a particle on the bottom rung, I give it a 2. So those are the 3 different possibilities. But now I have this nearest neighbor restriction in this funny picture. And if you just look at it for a second, what this means is 1 particle per square at most. So not only is it nearest neighbor, it's also forbids blockade. So it's like taking a longer blockade radius. So the blockade radius, if you wish, will govern all these. And that's the model. Well, that's the Hilbert space of the model. So this generalizes the chain, obviously. But the fact that this has something to do with this SP algebra and more generally these fusion categories gives you a lot of stuff. So anyway, so I'm going to use then from now on, instead of 0s and 1s and 2s, which have no intuitive value, I'm going to use T, E, and B for top particle on the top rung, E for empty, B for the bottom part of each rung. And so this configuration, again, if I didn't screw up, translates to that. Right.
So could you say maybe the adjacency rules, how they relate to the fusion again, or the adjacency?
Well, right. So this is now all the stuff I've swept under the rug. So now it's for the next 10 minutes or so, it's trust me.
Okay. Okay.
So basically the fact that I defined my Hilbert space in this way, and now, well, good, it's a good segue into this one, define this Hamiltonian. I will explain the Hamiltonian in a second. Define the Hamiltonian in this way gives me a ton of information. So in other words, there's a well-defined procedure going back to the 80s to take one of these fusion categories and get a bunch of nice stuff out. And that was one of the main topic of this paper I wrote with Ising and Meng, was that that you can get these topological defects, which I'll get to in just a few seconds.
But maybe the question is, you wrote some fusion rules first,
yeah,
example, and then there was the diagram. And
yeah,
is there a connection between the diagram and the fusion rules?
Yeah. Sorry,
so I couldn't get that connection.
Yeah, so the diagram. Where were we? Yeah, yeah. So the diagram. Here's what we want. Yeah, the diagram is literally just a picture of this.
Mm-hmm.
So if you look at, these are the fusion rules, right? And this picture just comes from these fusion rules, right? 0. So the picture means fuse with spin 1. So notice I take 0 and I fuse with spin 1. Well, the only thing I can connect, yeah, the only thing that appears in the fusion of the identity with the spin 1 is spin 1. So notice the only line on this picture that
so there is an adjacency diagram for each one that you choose
to
fuse all others with.
Yeah. Yeah, so there would be one for this. So I wrote, this is fusion with spin 1 and acting on the spin 1/2, which is actually how you get this the zigzag Ising that I wrote.
Okay, thank you.
Okay, so yeah. But boys, yeah, now it's giving me all this it gives me all this stuff that now the payoff is all this, the next 10 minutes or so that is the payoff, all this information I get that I'll go through quickly so that I can get back to the Rydberg. So, but let me waste another, well, hopefully not waste, spend a few minutes just saying the Hamiltonian you get. So it turns out it's easier to, instead of thinking in terms of top and bottom, is to take these linear combinations. And because we have only one particle per square, it's okay to do that. It doesn't mess up the restriction. If you relax this, all bets are off. I don't know what happens there if you take the anyway. So then we can write this diagram here again. So what this does is, like in the chain, annihilates and creates the plus particles. So another equal amplitude sum of a particle on the top and the bottom. So that annihilates it, and that creates it. First one annihilates it, second one creates it. So this just flips. If you have plus or minus near second neighbors, they can't be next to each other, but they can be next nearest neighbors. It flips both of them. And then this basically is just a number of the minuses. This thing says that, well, you get something non-zero if one or the other of the things 2 sides apart. So it's a next nearest neighbor interaction in the plus minus space. And again, there's no, even though this came from XXZ of this SP algebra. So this algebra, this Hamiltonian, again, it's not, this one's not obvious, takes you a little time to show. But this again, if that's S, the thing I just circled, that's P, then you satisfy this algebra. And again, there's no U1. But so one key thing I do want to say before I start to go quickly is there's no U1 symmetry, but there is a Z2 cross Z2 symmetry. It's not completely obvious, but if you think about it for a little. So there's obviously a symmetry that exchanges top to bottom in this. But because the flip is 2 sites apart, because of this restriction, there's actually, you can flip top to bottom independently on all the odd rungs or all the even rungs. So it's a Z2 cross Z2 symmetry, and I'm going to always have that symmetry. All right, so now I'm going to go fast for like 5 minutes and give a quick overview of the amazing things that SETI, well, it already gave me a Hamiltonian that's integrable for the ladder, and then it gives us even more things using this setup. So first of all, it gives you these maps, these non-invertible maps I mentioned at the beginning. So these are dualities in the sense it gives you these maps between the different models, right, called K, O, M, and D, and they commute with the Hamiltonian in the sense that, well, if you act on the Hilbert space before the map, then it's the same as the other Hamiltonian after the map. So I'm talking about this map here. So it just gives you these things absolutely explicit. So that's one of the payoffs, and that's what it did do. And so this is the story of paper with David Rogers. So I'll mostly skip this slide. The way to really write these things down explicitly is use these topological defects I mentioned at the beginning. And one thing I want to say, though, the defects exist without integrability. You do not need to impose integrability, and this is really going to be useful for us. So, so you can construct all these maps exactly, like I said a second ago. And in fact, when you do this, the diagram commutes, so it doesn't matter which way you go around. So you can map all these models, but these maps are not invertible. And for those of you who know what Kramer's 1A duality is, actually this map here is in essence between the XXE chain and that zigzag ladder I wrote down a little while ago. Is Kramer's 1A duality. And those of you who are experts in Kramer's 1A duality know Kramer's 1A duality is not invertible. It takes the low temperature phase of the Ising model to the high temperature phase, or vice versa. Well, you know that can't be invertible because the high temperature phase has a unique ground state, but the low temperature phase has two ground states. So it's not invertible. But this is always obscured for various reasons. But anyway, so, and you can see this formally by when you do the map and then do the map again, go back again, you get something that's a projection operator. And so that's the formal way to see it. And that's what we described at great length in this paper with David Rogers. What's more, you can get even a non-invertible symmetry. So basically, what turns out, if you start at the ladder, the Rydberg-blockade ladder, and you go to this zigzag ladder that I wrote down a while back, you go there, that's D, but then you go D dagger to go back again. It's D dagger. Then it turns out you get something else there that's non-trivial. Just work it out. And that by construction has to commute with Hamiltonian, so it's a symmetry. But then, again, you work it out, or actually this is known for more general things, it's fusion category stuff. This is actually like the fusion rule of a spin one representation. That's not a coincidence. And then you can see this thing is not invertible. It's satisfied. So this is very much akin to the Kramer's 1A self-duality of the Ising model, again, if you know how that goes. And what's even nicer, so now, okay, so I mentioned
so Paul, could I ask you also?
Sure.
So how to think about these maps a bit more concretely? Can I think of them as sort of linear maps of, states in the Hilbert space? They are just a big matrix, basically.
They are
the Hilbert space.
That's right. They are just linear maps on the Hilbert space. The one thing, though, is they're not typically not a product of local. They're a matrix product operator, not just a product operator. They're not a product operator, they're a matrix product operator. That's all. It's a matrix product operator. I mean, Kramer's 1. I mean, this was known before anyone said the words matrix product operator. So it is exactly that. And the benefit of the category is when you set things up this way, you get handed those for free. That's the content of my paper.
So just imagine I have two of these models in some finite size, right? So the Hilbert space is some, finite space, finite dimensionality. So K, for example, will be just some matrix.
Yeah, absolutely.
But it's like a rectangular matrix, because I think the Hilbert spaces don't have equal sizes. Or
no. So one of the things about non-invertible. So another way of saying it is these would have zero eigen. Your matrices, wouldn't be square and wouldn't have zero eigen. And even if you like pad them out somehow, then they have zero eigenvalues. So they don't map. They map subsectors to subsectors. I forget if I had a comment somewhere. But you can get all the things if you assume particular twisted boundary conditions. So it's still not one-to-one, but you can sort of do it sector by sector by mapping to sectors with twisted boundary conditions and things like that. So there is a way of getting them all, mapping them all. But
is there something like maybe a global symmetry that you gauge in one of them, and then
Yeah, exactly. So what happens in Kramer's 1A duality, for example, Kramer's 1A duality in its usual formulation only works if for states that are even under the spin flip symmetry.
Right.
But if you take the anti-periodic boundary conditions or twisted boundary conditions, then you can do the odd sector as well. But those are different. You can think of those are different theories. It's,
Right.
so you can do it sector by sector. And over the decades that people studied it, it was kind of done in this ad hoc, completely correct, but ad hoc fashion. But now we understand how to do it much better. More importantly, we understand how to generalize it, like to the example.
Okay.
So now what's also nice is I say XXE has U1 symmetry. These zigzag ladder and the blockade ladder don't. But under these mappings, so the U1 symmetry doesn't survive. If you do these mappings, you just get nothing. But if you square the U1 symmetry, so Q is the U1 symmetry of XXE, and then do the mapping, so this is just the mapping from XXE to Rydberg there. If you do that, then you can get something non-trivial. So this, again, annihilates half the states because that's a projection operator. That's the spin. That's the exchanging the top and the bottom rung symmetry. So it doesn't work on all states, but it is a symmetry. It just doesn't. It gives 0 on lots more states than the U1. Perfectly good symmetry.
I see. Very cool.
So that's another thing. So, okay, good. I want to get to the okay, good.
Good. Thank you.
Good. Okay, so now we can get to Rydberg. So now, okay, so that was quick. I hope I gave flavor. Again, stop to make sure if in case I said something with the non-invertible symmetries too quickly. Believe me, I'm not trying to derive any of this, but you just have to trust me that all this can be derived and it's all exact. And right. So now I'm going to use this mapping. So here, this is review. This is the phase diagram of the XXE chain going back for decades. Even the fancy CFT part, I guess. All right, so I mentioned CFT here. The phase diagram of the XXE chain is the following. If delta, the anisotropically, that was the coefficient of in front of the ZZ term. If that's in magnitude less than 1, the model's critical. It's described by, if you like, conformal field theory. It's described by a free boson. That's the radius. Free boson conformal field theory. So what happens when you take delta greater than 1? In my conventions is you get this is where the XXE model is anti-ferromagnetic. You get an ordered phase. You don't break the U1 symmetry, but you do get up-down sort of order. So it's an anti-ferromagnet, so you break translation symmetry like there. And over here is an exact ferromagnet. They line up, and so you get multiple ground states. So that's the XXE diagram. All right, but now because of this mapping, we can apply with care, we can apply this to the Rydberg chain. So you have to get the same diagram at the end of the day. I mean, the fact that it's critical or not doesn't depend on these details. We do have this exact mapping between the models. So it's critical between delta there. And there's a KT transition. I didn't say that before, but there's a KT transition at delta equals 1. But now we're going to interpret this differently. I'm going to explain that in a second, what happens there. This one is what happens. You get exact ground states, and you can go back and look at the Hamiltonian. This is exactly what happens, but you don't even have to just by knowing this exhibits. But the critical line here in the middle is still C equals, for those of you who know some CFT, it's still C equals 1, but it's an orbifold. So you've broken the U1 symmetry, and you also get a shift in the radius. That I don't have time to explain, but it's in the paper. But now what's cool is that this is a gapped region here, but you get a really unusual property. You get 3-phase coexistence. So if you now go to delta equals infinity, so way out here, you just look at that Hamiltonian I wrote down. You see there's 3 ground states. Either you have no bosons, or you get only plus bosons, and but they alternate every other side. So those are the 3 ground states there. So I'm running low on time, so I don't have time to explain how that is. I'll say a little bit more about that later. But but anyway, just trust me, that's what you get. But here's the interesting thing. All right, see, normally you would expect this is true at delta going to infinity. That's easy to check. But normally you expect, well, now we take delta lower, we lower delta from infinity. Well, what happens, one of the two, well, these are related by symmetry, but this one, the top one, is not related by symmetry to the others. So you expect one of them wins. So, and because no conventional symmetry relates them. And in XXE, indeed, there's only 2 ground states in XXE. basically these. But this self-duality that I mentioned quickly when I was talking about does relate all three of these. It's not obvious. And so, like you're saying, there's some matrix that multiplies this. You multiply that matrix on this state, and you get actually a linear combination of those two states. These three mix under that symmetry, form a triplet, if you wish, under that symmetry. So they have, so even though these are no longer the exact ground states once delta is not infinity, they still have to form a triplet under the symmetry. So this three-phase coexistence survives all the way. So that's pretty cool. So that we got out of it. So that you know there's three ground states for all delta greater than 1. And that you wouldn't get if you didn't do everything I just explained. Okay, so now, so that's what we learned from integrability.
Please allow me to ask a naive question.
Sure, sure.
So you mentioned that in between different models, there's a the mappings are not exact, basically.
No, they're exact, but they don't
invertible
all the spaces. Yeah, so good.
Yeah. No, so how does this non-invertible will affect this different phase boundaries?
Well, so it doesn't affect the phase boundaries because what happens, like I briefly mentioned, if you change the boundary conditions, you can then map all the states. And so changing the boundary conditions doesn't typically change the phase diagram, does it here? So the phase diagram stays the same. And because it's a state-by-state mapping, it basically, it maps half the states. So if half the states work, as long as you're describing physics in that sector, and then you change the boundary conditions, and then you look at the other sector. But again, the physics, as long as you're talking about things far from the boundaries, sort of the large volume limit, lots of the physics isn't going to depend on what you picked on the boundary conditions. Does that make sense?
I see. So I'm asking, how does that affect the division between different phases?
Yeah. Right. So it doesn't affect it because boundary conditions don't affect the phases. Because the physics, the phases are local physics and the boundary conditions don't affect them, even in a critical system. I mean, they affect precise properties, which operators you can have. They have all sorts of important and interesting effects on the physics, but they don't affect the gross phase structure.
Okay, I see. Thanks.
But I should say the phases had very different interpretations. So we saw that here. So in the XXZ, in the previous slide, what happens over here is, okay, it's just, broken translation symmetry, what you expect in an anti-ferromagnetic. There's no SE2 symmetry. All right. So that's fine. So it's fine. It's interesting. But here, this is very strange. So the interpretation is very different. But the fact that it has this order is not a coincidence. That the map tells you that.
Okay, thank you.
Okay, so now good. Well, we're running a little late now, but anyway, now I get to the full thing. So basically, we just take the big Hamiltonian and add arbitrary coefficients to all the terms, which we parameterized in this. The key thing is all we put in by hand is preserving that Z2 cross Z2, the changing the even and odd rungs, flipping from top to bottom. But we find for bonus is that not the self-duality, but the other non-invertible symmetry, the remnant of the U1. All right, so first thing you do. So the integrable line corresponds to T equals W equals 0. And this parameterization, why we wrote it in this way. So the first thing you do, right, you throw it on the computer and just see what happens. For this thing. So this is a cut, and this is the W equals 0 cut, so T and delta. Delta is the XXC parameter, so that we're still keeping here. So the integral line is the line through the middle here. Oops, I shouldn't have done that. So anyway, so this is what you get. So looks like you get a bunch of phases. So now in my last sort of -3 minutes, I'll try and tell you something about how we get these phases. So again, let me go quickly back to the Potts thing. So since I didn't explain this in the beginning, I'll do it quickly. You get these phases where you get order and the only symmetry that's spontaneously broken because it's the only one you have to break, is this translation symmetry. And then here there's this phase coexistence line here, that just like we may have in the other. So it's a first order transition between disorder and Z2 order, and along that line they coexist. It's also integrable, the chain model. And you get a second order transition and this chiral transition, post transition. So that's a quick view of that. And basically we get all that here and then some. So since I'm low on time, I'll go through really quickly how we get some of this stuff before giving you the results. So you can go to various limits. So like you go to delta plus t positive and you see that term dominates. And so that means you want to make this 0. So that means sites must all be, this is the density operator for empty rungs. So this means if you have this be 0, that means all nearest neighbor rungs are empty or they're all occupied. So these are basically the two possibilities. And so you can get plus or minus. So you basically get two Ising models, and you can see that the other things do. Another thing, if I take this limit, delta minus t, 2t large and positive, this term wins. So you forbid minus particles, right? Because I want to make this 0. So you forbid minus particles, and you just get a special case of the chain. It's the u equals minus v. So quickly, it's the line. It goes like that. So again, now we can map out the phase arc. So this will be the last, well, one more slide where I map out this diagram, 2 slides where I map out this diagram. Right, so that's the picture I showed thing. Okay, so that's exactly what I showed. Now we can map this out. All right, so that we know from integrability, that line is critical. We know there's 3 exact ground states there from integrability, and we know that's now this phase coexistence. So then knowing that, all right, it's pretty easy to guess, and perturbation theory that I just outlined shows you this phase is Z2 ordered, where again, it's translation order. The ground states look like that plus its translation. And here's the disordered phase because the ground state off at infinity is there. So it stays disordered. So now what happens there is I said quickly, well, this turns into 2 Ising models. And so what you get, Ising order, you break this Z2 order. So the ordering pattern is empty, particle on the top rung, empty, particle on the bottom rung, empty, particle top rung, and so forth. So that's the order there. So you break this Z2 cross Z2 symmetry here because you got 4 ground states, the translations of that. So that turns out that's called the dihedral group when you have both translation symmetry in that. Up here is Ising order. Again, you get 2 ground states, but here it's dominated by empty and then the minus, the top minus bottom. So now there you get the Z3 phase, but one of the things now you get that, well, first of all, because we have a Z2 cross Z2 symmetry, this wasn't in the chain. But now we get something even funnier than the chain. We get 2 Z3 phases, but this one's dominated by E minus, so that's top minus bottom. This is top plus bottom. And there's 2 phases, and there's a first order transition, which you can see a little here with the heat thing. And the non-invertible symmetry distinguishes between the 2. And then the PXP model, which is way off there because you like that. All right, so last slide. So now just to describe the transitions, well, these are Ising squared. Out here, comes from just Ising transition. So these are critical, which is nice. The coexistence line I talked about there. So blue dashed is first order, red is second order. And you find both these chiral and post transitions like you get in the chain, which is pretty cool. This is the sort of a full critical line. But then now, there's the Ising squared, I said. But now you get something pretty cool. You get a small critical bubble. So let me explain where that comes from. So you get 2 relevant operators. We can do conformal field theory. I said I was going to do field theory at the end. So finally, I do some field theory. You can tell because of this exact mapping, we know which conformal field theory it is. And we can tell what operators are relevant. And basically, depending where you are on the critical line, you get different stability. So there's even a region where where there's no relevant operators, the critical line. So you get a whole critical bubble. Obviously, it's very small unfortunately. The way it works out is delta is only a very small region, but it's there. We saw it numerically. Here you get, in a pretty big region, you get a critical plane. Here there's two relevant operators, so you can't tune them away. And so basically it's a critical line only in the plane. That's what happens in, sorry, only the critical line. That's what happens. Right. Sorry for running a little over. I'll just flash my conclusions. You can ask me about them if there's anything. Anyway, thank you for listening.
Yeah, thank you very much, Paul, for this really amazing talk. Are there any questions? So please just unmute and yeah, go ahead.
Right. So I just want to understand this this point about topological defects being used to produce mapping. So if I understand correctly, and correct me if I'm wrong, the way I'm understanding it is essentially like in the TFIM model, the transverse field Ising model, there's this duality which maps J to H, like the transverse field to the
That's right. Right, that's the thing I call Kramer-Schwann duality. That's right.
Right. So is what you're mentioning with the topological and the boundary condition point, you're saying like similar to how in the TFIM you go from the smooth boundary conditions to the rough boundary conditions, and this kind of a picture. Like if you're working in finite systems, there's this the change of boundary conditions things that happens.
Well, yeah, that's in that case it corresponds to periodic and anti-periodic. If you're doing in terms of, say, the fermions or the both, well, if you're doing field theory, it's periodic or anti-periodic. In the defect language, it corresponds to putting a spin flip. It corresponds to putting a spin flip defect. In terms of the Hamiltonian, it corresponds to having one bond where you reversed the sign of J. So that's the anti-periodic boundary condition. And so then you get the odd, so that's the other sector. So a subtlety I didn't mention is if you do this mapping with open, instead of periodic, you do it for open boundary conditions, it maps between fixed boundary conditions, so say all up, and free boundary conditions where
exactly, yeah.
Whatever, maybe that's what you were, is that what you were referring to?
Yes.
Yeah, right. So if you do the duality there, right, it does that. Which you can all handle all, and I just for simplicity ignored that, but it all, and then the answer to the other question earlier, yeah, so the boundary conditions are interesting and important, and I spent a lot of my life on them. But for the big properties I'm talking about today, don't want that.
Right. Okay, cool. Thank you.
Any other questions? So if I may just ask you to comment a little bit again on this critical bubble. I didn't follow exactly.
Oh yeah, sorry.
So
since I got so rushed. Yeah, let me. So let's go back to this picture there. Right. So what happens here? So we have a transition line that we know exactly. So it's setting t equals w equals 0. The point is now this is just a slice. So what happens now if I turn on W as well? Does the critical line go away or not? And so then but the point is, because we know exactly what field theory this is. It's this boson field, orbifold field theory. No matter what, just we know some field theory. You can look at what you know, then all the relevant, all the operators in the field theory. And then you just ask, what are the symmetries? So you have to just then sit down and look at what are your symmetries in the lattice, including this non-invertible symmetry that survives throughout this whole 3D phase diagram. And then ask, is this operator allowed to be added to the Hamiltonian or not? Mm-hmm. And so what you find is it depends on the value of delta. And there's a region where there's no relevant operators. The symmetries, the non-invertible symmetry plus the Z2 cross Z2 forbid all the operators. Mm-hmm. So therefore, you perturb in W or T, and it's still critical because there's no relevant operators consistent with the symmetries. And so you get this small critical bubble.
So it's like a Lattinger liquid, but
Yeah, yeah,
model that doesn't have any kind of global U1
yeah, that's right.
symmetry.
That's right. It's without a U1, right. That's right. But there's no relevant operators. Yeah. I mean, yeah, that's right. Which is kind of neat. The Z2 cross Z2 and this funny non-invertible symmetry are enough, which, I mean, remember the non-invertible symmetry is a remnant of the U1, but it's not as strong. That's why it's not the whole line. It's only there. So yeah, and then what happens here for ways is there's only one relevant operator. So that means you can tune T and W to cancel the relevant one. So this will go up into some plane that you can check numerically. And then further over, there's two relevant operators. So this line is just a single line in this big picture. The transition is first order.
Okay. So, but maybe just to understand a bit more. So, is the U1 symmetry of the XXC completely lost, or is it maybe just hidden, that is not manifest? Well,
the U1 is lost. Now you square the generator. So that's not really U1 anymore because it's the square of a generator. And you transform that, and that will transform. And so that's what's left, which I think is a new result. So if you're familiar with it, it's the same story. If you're familiar with the Ashkin-Teller model, which is two coupled Ising models, which can be related to XXZ in various ways. The same thing happens there. You've broken the U1, but this relic. As far as I know, we're the first to sort of discuss this explicitly. It wouldn't surprise me if someone else had, but as far as I know, we're the first people to really write down the formula.
This is really cool. Very nice.
Yeah. So it does buy you this critical bubble. Yeah. We were excited, and then you work out, oh Jesus, it's only this tiny region. It's 0.94 to minus 0.94 to minus 1. But hey, take what you can get. It's there, and it was really hard to see numerically. Luisa had to really work hard. Well, at least I wouldn't say I wouldn't. Well, I bet my life on the theory. The numerics, I think, were pretty convincing. But if I didn't have the theory, I may not have believed in numerics. But at least we saw numerics that pretty strongly. Right. So that we're certainly consistent with it. I think pretty strongly hinted. If you didn't know about the theory, you would at least take it as a good hint. And the theory, I think, is bulletproof. So.
Right. Excellent. Wow, this is really amazing. This is like really, your talk was really mind-blowing to me.
Well, thank you. Appreciate it.
Any other question from the audience, since I see still some people?
Yeah, I didn't put anything provocative in my conclusion. Sometimes I put something really provocative in the conclusions that will anger someone. Get them to ask me an outraged question and let me talk for another 10 minutes explaining what I meant. Anyway, I didn't do that this time.
Excellent. All right. Thanks a lot, Paul.
Well, thank you so much. I really enjoyed it.
Yeah, thanks a lot.